Everybody, welcome back to section 9.6, talking about factors that influence chemical reaction rates. So a chemical reaction rate is the rate at which reactants are consumed or products are produced in a given amount of time in a chemical reaction. So when we're talking about the reaction rate, we're essentially talking about how fast are reactants converted into products. So there's 4 factors that influence chemical reaction rates we're going to be talking about. The first one is the physical nature of the reactants. And when we talk about the physical nature, we're talking about the subdivision, like how broken up or how small of parts are the reactants in, and the physical state. We're going to talk about the reactant concentrations, reactant temperature, and the presence of catalysts. So the first factor that can influence reaction rates is the physical nature of the reactants. So this is both the physical state is or are the reactants present as a solid, a liquid, or a gas, as well as the subdivision or the particle size. So in order for a chemical reaction to happen, remembering back to collision theory, the reactants have to collide together, and they have to collide together in the right orientation, and they have to overcome the activation energy. So for the reactants to be able to collide together, they have to be able to come into contact. So reactants that are solids, where the reactants are held together in a fixed position by very, very strong cohesive forces, they're not able to readily mix and collide to form products. And so the reaction rate of reactants in the solid state tends to be much slower than the reaction rate of reactants in the liquid or the gases phase. So the diagram here on the right shows the relative reaction rate based on physical state. So solids tend to have the slowest reaction rate. And that's because, again, in a solid, the particles are held together in a fixed position. So if we have reactant A reacting with reactant B, and they're both solids, it's going to be really hard for these reactant molecules or particles to collide with enough energy to overcome the activation energy and in the right orientation. So because of the physical state, this reaction is going to be slower versus if these reactants were in the liquid state where they can freely move around each other. Diagram here of a liquid state, the particles are still touching, but they're able to move around each other, which means that they're more able to collide with other reactants also in the liquid state. They can come together and collide and move around each other, so that reaction rate will be a little bit faster. And then when reactants are in the gas phase, because gases move completely independent of one another, and they move very quickly, they have a lot of kinetic energy. The cohesive forces are very, very low when substances are in the gas phase. Gases will have the fastest reaction rate. So slowest, kind of medium, and fastest. So the physical state, whether something's a solid, a liquid, or a gas, will impact the reaction rate. With physical states that have a higher degree of cohesive forces, like solids having slower reaction rates compared to reactants that are in physical states that are dominated by disruptive or kinetic energy forces like gases, and then liquids are kind of in the middle. The other factor relating to the physical state that will influence the reaction rate is the subdivision or the particle size. And this is especially important for solids because the smaller the particle size, the more surface area you have. And so the more surface area you have, just the higher the chance there is of particles interacting and colliding in the right orientation. If you kind of think of it like, we draw a diagram here. All right, you have one cube of reactant colliding with one other cube of reactant. There's only one way if they have to collide this way and this way to be in the right collision orientation. There's only one way that could happen. But if you break both of these up into smaller pieces, right, each piece could collide with another piece of the other reactant. So because of this, there's a lot more potential collisions which means you're likely to get the collisions happening in the right orientation with enough energy to overcome the activation energy to get a reaction. So having smaller pieces, increasing the subdivision of your reactants, can also speed up the reaction rate. So in summary, when reactants are all in the same physical state, the reaction rate is generally faster between liquid or gas state reactants than between solid state reactants. Solids are going to be the slowest, and gases are going to be faster. And then the smaller the particles, the more broken up your reactant is, the more chance it has to collide with other reactant particles to facilitate that chemical reaction, with the reactant particles colliding with enough energy and in the right orientation to get a chemical reaction. This is why, if you think of like dissolving a sugar cube, I'm really enjoying drawing cubes in here, right? You have a sugar cube and you try to dissolve this in a cup of hot water. It's going to take a lot longer to dissolve the cube of sugar versus if you put in granulated sugar, because the granulated sugar has a lot more surface area to dissolve into the solution versus the sugar cube. It's the same thing with reaction rates. You increase the surface area, you increase the likelihood of a collision happening in the right orientation and the reaction proceeding. Okay, so that's our first way we can influence reaction rates. Number two, we can change the reactant concentrations. So if you increase the concentration of a reactant, it's going to cause an increase in the rate of the reaction. And what's happening when you increase the concentration, as shown in the diagram, is that you're just increasing the likelihood of reactant molecules or particles colliding. So here we have few molecules, a low concentration. So there's going to be few collisions between these reactant particles. It's like it takes them longer to find each other and collide in just the right orientation. So the rate of reaction is going to be relatively low. But if you increase the concentration of your reactants, they're going to collide a lot more often. And because you're going to get more collisions, you're going to get a faster rate of reaction. So increasing the concentrations of your reactant is another way to increase the rate of the reaction, the speed at which a chemical reaction occurs. Number three, we can change the reaction temperature. So the reaction rate is going to increase as the temperature of the reactants increases. And what's happening at the molecular level is that as you increase the temperature, you're increasing the kinetic energy. And so all of the reactant particles or molecules are going to be moving faster. And so you're going to have more collisions between them in any given amount of time. And because you're going to have more collisions, you're going to have more collisions that happen in the right orientation preceding a chemical reaction. So I love this online simulator that kind of illustrates this. I put the link in the slides, and let's go over to that simulator to show it. So this will demonstrate kind of what we're talking about when we increase the temperature, that you get more collisions between reactant molecules. And because you get more collisions, more of those collisions are likely to be in the right orientation to allow a reaction to proceed. So we have blue reactant and green reactant. And if we have a low temperature, we let them mix. You can see there's, some collisions, but they're not mixing and colliding very readily. But if we increase the temperature, everything moves faster. And so you're getting just more collisions per second or per minute, which increases the reaction rate. Even higher, they really get going. So increasing the temperature will increase your reaction rate because it facilitates the reactant particles colliding more often. And when they collide more often, they're more likely to have a collision in a given amount of time that's in the right orientation with the necessary amount of energy, the activation energy, to get a reaction to happen. Okay. Our fourth way that we can influence the chemical reaction rate is by using what's called a catalyst. So a catalyst is a substance that increases a chemical reaction rate without actually being consumed in the chemical reaction. So what a catalyst does is it increases chemical reaction rates, makes them go faster by providing an alternative reaction pathway. And what these alternative pathways have is a lower activation energy than the original uncatalyzed pathway. The way I think of it is like if you want to go from Sacramento to, say, Lake Tahoe, you could drive through the national forest, taking Forest Service roads the whole way, right? And you'd get from point A to point B, from your starting point, your reactants, so to speak, to your destination, your products, but it would take a really long time. Or you could take kind of the faster route, the catalyzed route, which is like taking US 50 or Interstate 80 to get straight there. So that's kind of like the difference between with and without a catalyst. Your starting points and your ending points, your reactants and your products are the same. It's just with a catalyst, you get there the fast way instead of taking the slow way. So chemically speaking, without a catalyst, if you're combining X plus Y to make the product XY, it could be a relatively slow reaction. But with the catalyst, shown here as a highlighted C, what a catalyst can do is grab one of the reactants and kind of get it in the right position to collide with the other reactant in just the right orientation. It's kind of like a matchmaker getting everything lined up so that when they do collide, they're ready to have a reaction. And that helps speed up the reaction rate. So here we have step one. Your catalyst essentially grabs X and might temporarily bond to it to get it in just the right position. So that, say, if this side of X needs to participate in the chemical bond with Y, this side is exposed and ready to go. And then the catalyst will bring the catalyst compound or complex together with the other reactant to get X and Y to react. So you end up with the same product as you would with the uncatalyzed reaction. And at the end of your reaction, your catalyst is returned to its catalytic state. So oftentimes in reactions facilitated by catalysts, at the end of the reaction, you can reuse or recycle that catalyst and use it over and over again. And this is exactly what we did in exercise 3 in the lab. If you remember in exercise 3, we decomposed hydrogen peroxide using the catalyst manganese oxide. And manganese oxide helped facilitate the decomposition of H2O2. So we produced water plus O2. We balance this. Manganese oxide at the end of the lab could have been recovered from the reaction vessel. It was a black powder and it was there at the beginning. We added it to speed up this reaction. And at the end, it was still present and we could have filtered it out and continued to reuse it. So catalysts reduce the activation energy for chemical reactions. And by reducing the activation energy, overall, you get a faster reaction. So the catalyst doesn't chemically participate in the reaction. It's not part of the reactant and it's not part of the products. It just helps bring the reactants together in the right orientation, the right collision, so that the energy it takes for them to have a reaction is a little bit lower. And again, catalysts are often able to be recovered after the reaction and then used again or recycled. Catalysts are incredibly important in human health. Enzymes are catalysts. They're proteins that act as a catalyst. And in the human body, enzymes assist in nearly every reaction. So when you metabolize foods and break them down, those are enzyme catalyzed processes. When you produce ATP, one of the main energy sources for the body, those are all catalyzed processes. Essentially everything that happens in our bodies happens because there's an enzyme, which is a type of protein that catalyzes a chemical reaction that assists in that reaction. So when you go on and take bio courses, especially biochem courses, you'll get a lot more into this. It's awesome stuff. If you ever want to talk about it, just drop into office hours and I'd be happy to. So this is a summary slide to summarize this last section that we just went over. So factors that increase chemical reaction rates. We've got 4 factors. Number 1, you can increase the state of subdivision or you can change the physical state. So when you increase the state of subdivision, you increase the surface area, which increases the likelihood of collisions between reactants. And when you change the physical state, gases have more kinetic energy, they move freely around, so they're going to have more collisions versus a physical state like a solid or a liquid where they're held together by strong cohesive forces. Second way, you can increase the reactant concentration. By increasing the number of reactant molecules, you're more likely to have collisions between the reactants, and you're also more likely to have more collisions per second. And so overall, your reaction rate will increase. Number 3, you can increase the temperature. So this increases the molecular energy, the speeds of all the particles moving around. And so collisions are going to happen more often. And you're more likely, because you're having more often collisions, for those collisions to happen in the right orientation in a given amount of time, which means your reaction rate will go up. And the fourth way you can increase the rate of a chemical reaction is to add a catalyst. And so a catalyst will lower the activation energy by providing a more efficient reaction pathway. Again, you can kind of think of like driving to Tahoe. You could take the little tiny Forest Service roads to get there, but it would take a long time. Or you could take the catalyzed path and jump on the freeway and be there in, a little bit over an hour, maybe 2 hours if you're not speeding. So by adding a catalyst, you get more reactant collisions, which then meet the new lower activation energy requirement to produce more product in a smaller amount of time to increase the reaction rate. So that's a summary of the 4 factors to increase chemical reaction rates. We'll come back next time and talk about chemical equilibrium. Thanks.